Okay, so now let's look at heat from a physics point of view, and we'll start with kinetic theory. Kinetic molecular theory basically describes or explains all the effects produced by heat. And I just pointed out four characteristics that can summarize it. So for instance, particles are held together by electric forces, or electrostatic forces, kind of like static electricity. Particles are in constant motion, and they therefore possess kinetic energy, okay, energy of motion. So they're always moving, and when they collide with each other, instead of losing energy, they transfer energy. Okay, so when a car runs into a wall, energy is transferred into the wall. If there's enough energy, it will break the bonds and break the wall. Finally, when molecules absorb energy, they become faster. When heat is removed, molecules become slower, okay, because kinetic energy is either increasing or decreasing. So for instance, if you were to heat a cup of water on a stove, you're inputting energy into the system, so the system's absorbing energy, increasing the kinetic energy. Molecules move around faster. If you continue to do this at 100 degrees Celsius, the molecules will be moving fast enough that they'll break these electrostatic forces, and they'll be far enough that they'll phase change into a gas. Okay, so that's basically kinetic theory. Okay, if you want to speed up a reaction, okay, one way is to increase the motion of the molecules, okay, by introducing heat. So you can watch that video down there explaining kinetic molecular theory in a different way perhaps, but let's move on to some topics. So this video will cover some of the topics in kinetic theory, and I need to get to a few calculations as well. So certainly, I'm assuming that you've read through these already. Thermal energy is something we'll use this term a bit, and basically it's the sum of the kinetic and electric potential energies. Okay, so the kinetic energy is motion. The electric potential energy will be the electrostatic energy between objects or molecules. A hot object has more thermal energy because it has a higher kinetic energy, right? And it has higher electric potential. Let me just switch here to red. And a colder object will have lower thermal energy, okay, because it has lower kinetic energy. Now let's get to let's define temperature. Okay, it might seem intuitive, but temperature actually needs a definition, or requires a definition. And if you look up temperature, it will get more and more how do I say this, like syntax heavy if you go down the tubes on Wikipedia and look at how to define temperature. I'm just going to briefly qualitatively define this. It's basically the measure of average kinetic energy of the molecules of a substance. The key is this word, average. Okay, it's the average kinetic energy. So you can have a molecule flying at a ridiculously high speed, but the average of that area can be a really low temperature. We see this in the upper atmosphere, okay, the upper atmosphere, where the air is so is not dense at all, right? Molecules are spread out. However, they're getting so much radiation because they're so non-protected, right, in the upper atmosphere, that some of the molecules can be traveling at very, very high speeds and can have individual temperatures of 3,000 degrees Celsius. Okay. However, if you were to be up there, physically, if you were to be up there, okay, temperature loses meaning. It would actually be really, really cold because on average, there's not that many things going on, not too much kinetic energy happening. Here on Earth, okay, on the surface, when you take the temperature of a lake, okay, lots of molecules bouncing around, you're taking the average temperature, okay, the average kinetic energy of the molecules. That's why if you take the thermometer and you keep increasing in depth, getting lower and down, you'll get colder because there'll be radiation, sun's rays are not hitting that area of water, and therefore there's less kinetic energy. Now, and this is going to be an important topic, thermal equilibrium is said to be when two objects have the same kinetic energy. And this is a fundamental and natural process that will occur. Take a look at this picture. If you're to place, let's say this is some kind of rock in water, the rock's at 10 degrees Celsius, water's at 20 degrees Celsius. Over time, here is thermal equilibrium. So what this means is eventually they'll be the same temperature over time. So what's happening there? Well, basically the water, okay, is energy is flowing naturally from a hot object to a cold object. That will be a law that we'll describe later on here. So here's some basic facts of how we measure temperature. We use thermometers. We either use alcohol or mercury thermometers usually. If we were to do this in lab, we would have alcohol thermometers in the schools. Mercury is poisonous, so if you break it open, try not to get it on your hands. And obviously don't consume it. But they have different properties. Alcohol thermometers can't particularly measure high temperatures because of the boiling point of alcohol is lower. These things are pressurized though. They behave strangely though if you exceed certain values, or if you dip below certain values. Okay, so mercury thermometers can't measure really low temperatures. So now we're going to get to some calculations because we're going to get to temperature scales. There are three typical temperature scales that people use. That would be the degrees Celsius, degrees Fahrenheit, and Kelvin. So, and one of those scales is kind of silly, but we're going to study all of them. So, let's just introduce a topic called absolute zero before we do so, because one of the scales will use it as a reference point. Absolute zero defines no molecular motion. Okay, in other words, zero kinetic energy. Okay, and no thermal energy. There you go, no thermal energy. It's impossible to reach absolute zero, and I'll explain why in another video. However, that if that point were possible to get at, that would be a state where there's no movement at all, no movement whatsoever. So, and before we get on, so you can watch this little video about absolute zero, which is kind of interesting. Before we move on, just a quick note on significant figures. For sake of simplicity, we're always going to consider the temperature is at least two significant figures. So for instance, if I report 40 degrees Celsius, it's not one significant figure, it's going to be two significant figures. This is because, I mean, you're not going to have a thermometer that is going up by tens. Okay, it's going to be going up by ones at least. Okay, so that is an assumption hopefully you've made note of. So now let's go do some examples, and that's how we're going to end this video. Fahrenheit, Celsius, and Kelvin. So the Americans, or in the US, they use Fahrenheit. There's perhaps a few other countries that do as well. And Fahrenheit, I believe, is basically relative to body temperature, and they assign that to be 100 degrees Fahrenheit is the average body temperature. Okay, so that's the reference point, is body temperature. Celsius, degrees Celsius, is typically in the metric system. Its reference points are to do with water. Okay, 0 degrees is the melting and freezing point of water. 100 degrees is the boiling point of water. So everything is in relation to water. Okay, Kelvin will be the SI unit for temperature, and it's relative to absolute zero. So there are no negative values for Kelvin. And that's because you can't go below absolute zero. Okay? So, 0 Kelvin is exactly, let me just see here for a second. 0 Kelvin is, if you're to look at these temperature conversions, okay, it will be negative 273.15 degrees Celsius. That would be what absolute zero is. Here are the three conversions that you're going to use. Okay, so you should copy these down, put them on the reference sheet. So degrees Celsius, you can see why Fahrenheit is kind of a goofy way of measuring things, because it's difficult to convert between Celsius and Fahrenheit mentally. But Kelvin and Celsius are quite easy to go between. So if you do some examples, take a look at these. You're converting units. Notice how there's no direct formula to go between Fahrenheit and Kelvin. So perhaps let me just show you that you can very easily make one. It's not common, but you could simply solve for Celsius in this one and plug in to Fahrenheit, and you get something like this. So you get Kelvin minus 273.15 plus 32. That will go between Fahrenheit and Kelvin. But you can do it in 2 steps. So we'll finish off the video just by doing some conversions. So 112 Kelvin to degrees Celsius. Well, when you look back, we know that Kelvin is equal to degrees Celsius plus 273.15. So Kelvin is equal to degrees Celsius plus 273.15. You're given Kelvin in this question, so you're given 112 is equal to degrees Celsius plus 273.15. Therefore, you're going to subtract. Over, and you get negative 161.15 degrees Celsius. If you're to round this to the correct number of scientific notation, or sorry, significant figures, you're going to get the following. Okay, and of course, my last question is going between Kelvin and Fahrenheit. Let's do this in 2 steps. So your goal here, if you didn't introduce another formula to go between Kelvin and Fahrenheit directly, you'd go Kelvin to degrees Celsius to degrees Fahrenheit. So to go between Kelvin and degrees Celsius is just the same as above. You go 212 minus, so degrees Celsius is equal to 212 minus 273.15, and when you do that, you get 61.15 degrees Celsius. I'm not going to round because it's an intermediate step. Then I would plug it into my degrees Fahrenheit formula, which I forget. This is why it's inconvenient. So here it is right here. 9/5 times degrees Celsius plus 32. 9/5 times degrees Celsius, which in this case is negative 61.15 plus 32. And there you have it. So 9/5 times negative 61.15. Ooh, plus 32. There we go. Comes out to be negative 78.07, which you round it to be, we want 3 significant figures, so it's going to be negative 78.1 degrees Fahrenheit. And there you have it. So that's how you're going to do the various temperature conversions. In the next video, perhaps I'll talk about the laws of thermodynamics. Please read through them beforehand, and then we'll talk about them, and we'll move on to the next section.